I'm Mark Rosengarten. Welcome to the second annual Monster Chemistry Review. This is the Period 1 edition. And that's Period 1. The students have all put questions, in some case more than one question, on a piece of paper and put it in this here box. I'll be selecting from this box and we'll be answering your questions about chemistry because you all have a final exam tomorrow.
Final exam!
Woo! So, the first question is, which substance yields H plus aqueous as the only positive ion in an aqueous solution? The answer is 3. Why? Well, very simply this. An acid is anything that gives off H plus when you dissolve it in water. And as you know, acids have hydrogen. Exactly. Now, if you take a look at each of these choices, they all have hydrogen in them. The difference is they all have hydrogen in them. The only thing is that acids usually start with hydrogen. Now, none of these choices start with hydrogen, you know, like HCl, H2SO4, H2CO3. So when in doubt, what we need to do is go to the reference table, specifically reference table K. We could also use reference table R for this. When in doubt, always go to reference table K because this has a list of the common acids in it. And you'll notice that they all start with H with one exception, ethanoic acid. The H that comes off is the H at the end. And if you remember from organic chemistry, organic acids end in COOH. And since by definition an acid gives off H plus when you dissolve it in water, since that is an organic acid, by definition, this is what gives off H plus when you dissolve it in water. Question number 2. Electron pairs shared in covalent bonds. How to determine. Okay, so in other words, how do you tell how many pairs of electrons are going to be shared in a covalent bond? Okay, let's take a look at that. It all comes down to the number of valence electrons that the atom has available to bond. And if you take a look at the periodic table, you can find the valence electrons down in the electron configuration. And what I'm going to do is I'm going to put 4 different elements down: carbon, nitrogen, oxygen, and fluorine. Carbon has 4 valence electrons, nitrogen has 5, oxygen has 6, and fluorine has 7. So if we take a look at that, carbon, nitrogen, oxygen, no! Thank you. And fluorine, I didn't realize I was zoomed in that much. Carbon has 4. Now there's 2 ways of doing carbon. The traditional way is you fill up the S's first and then you fill up the P's, like that. Or you can also draw it like this, which is how carbon bonds to form organic compounds. Nitrogen has 5 valence electrons, S up, down, P up, and up. Oxygen has 6, S up, down, P up, down. And fluorine has 7 valence electrons, up, down, down, down. Now the number of bonds that an atom can form is determined by how many unpaired valence electrons there are. For example, in this form, carbon can form 2 covalent bonds. How many can carbon form here? 4, right. Nitrogen can form how many covalent bonds? 3. And oxygen can form 2, and fluorine can form 1. Now that means that when nitrogen bonds to another nitrogen, they're going to bond using a triple bond. So these 3 unpaired electrons will pair up with another nitrogen's 3 unpaired electrons, and they will share 3 pairs of electrons, each pair representing a covalent bond. In fact, we could also draw it as that because it's a triple bond. Each pair of shared electrons is a bond. For oxygen, we can draw it like this. Since oxygen has 2 places where it can bond, oxygens will share 2 pairs of electrons to form a double bond. And fluorine only has 1 electron to share, so when it bonds with itself, it can only form a single bond, where this unpaired valence electron is shared with another of fluorine's unpaired electron. And what happens is, when they pair up, that forms a covalent bond. So you can tell how many covalent bonds you're going to form based on how many unpaired electrons you have, and the number of pairs of shared electrons is the same as the number of bonds you form. The reason we do it this way is to keep symmetry. This way we can see this molecule has two lines of symmetry, and it's a nonpolar molecule. Also, take a look. These two electrons are here, and these three are kind of symmetrically there. So if we take another nitrogen, boom, 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 these two will pair, these two will pair, those two will pair, and leave them the paired electrons on opposite ends of the molecule. Let's move on to the next one. 47 from the fake final. This, of course, is the stoichiometry question. And what I'm going to do is I'm going to show you a simplified version of the stoichiometry question to start off with. I'm going to use a different example than this since we've already done this one. The way it works is this is the question, right? This is the 47 we're talking about? Whoever wrote the question? Yeah? Okay.
I wasn't here when you went over it, that's why I asked.
I'm sorry?
I wasn't here when you went over it.
Exactly. Okay. Here's a simple way of looking at it. Let's suppose we have the reaction Al plus O2 forms Al2O3. And we balance it by putting a 2 there. And no, we don't balance it by putting a 2 there. Yes, we do. We put this here and we put a 4 here. Okay. Now, the importance of putting the numbers here is it tells us the ratio of aluminum to oxygen needed to make 2 moles of aluminum oxide. 4 moles of aluminum and 3 moles of oxygen will always make 2 moles of aluminum oxide. If I have 8 moles of aluminum, then I'll need 6 moles of oxygen and we'll make 4 moles of aluminum oxide. 4 to 3 to 2 is the mole ratio that we're going to get. Now, let's suppose we said we have 3.0 moles of Al, aluminum. How many moles of aluminum oxide can we make from that, assuming we have enough oxygen to do the job? And so what we do is we set up a ratio. We do 3.0 moles of aluminum, and then we multiply it by the ratio between aluminum and aluminum oxide. But we have to choose which goes where carefully. We want to cancel out aluminum. So we need to put the coefficient of aluminum in the denominator. This way, when we multiply it through, the aluminum will cancel. And then we want to put the aluminum oxide's coefficient, Al2O3, on the top. This way, when we're done, like I said, aluminum will cancel and we'll be left with moles of aluminum oxide. And if we do the calculation, let's see, 3 times 2 is 6, and 6 divided by 4 would be 1.5 moles of aluminum oxide. Now, I could have taken this further. I could have, instead of giving you moles, I could have said, let's say we have 73.2 grams of aluminum. And instead of moles of aluminum oxide, let's say I wanted to find grams of aluminum oxide. Well, all I have to do is take the grams, divide by the formula mass to get the moles. And then on this side, once I have moles, I just multiply by the formula mass of this, and that'll get me grams. So this is really the heart of the whole problem. In fact, on the Regents exam, this is the only part that's testable. On the final, being able to convert from grams to moles first, and then from moles to grams when you're done will also be part of it. How to determine shift in a reaction that has reached equilibrium. So this is a Le Chatelier's principle question. Let's take a look at this sample equilibrium. Let's suppose, I'm just going to put a generic up here. 2A gas plus B gas plus heat forms an equilibrium with 2C gas, like that. So 2 moles of whatever this gas is plus a mole of this gas, and the forward reaction is endothermic, and it forms C. But as it forms C, C gradually breaks down to form A and B again, and eventually the rates are equal, so you reach equilibrium. Le Chatelier's principle states that any time you apply a stress to a system at equilibrium, the equilibrium will shift in whatever direction reverses the stress you just put on it. For example, if we add A, the stress is, oh my God, there's too much A! We gotta get rid of it! And the only way to get rid of A is to react it with B to form more C. So what will happen is A will go down, B will go down, and C will go up as a result of this. If we add B, the equilibrium is like, we gotta bring that B back down! And the only way you can do that is to get rid of it, but using up B by reacting it with A. So A goes down, B goes down, and C goes up. If you remove A, the equilibrium will be like, hey, where'd all that A go? And so the equilibrium will shift in a direction that will bring A back up again. We'll use up some of our C to bring A back up. So what will happen is A will go back up, B will go back up, and C will go down as a result. You can see the result of your shift is going to be to reverse whatever it is you did. You add A goes back down. Add B goes back down. Remove A goes back up. If you increase the temperature, the equilibrium is going to say, it's too darn hot, it's too darn hot, and say, we got to get rid of some of this excess kinetic energy. Because temperature is kinetic energy. And how do we get rid of kinetic energy? What do we convert it into? Convert it into potential, and you do that with an endothermic change. The extra heat is absorbed in the chemical bonds and stored. Or you could say, it's too hot, we got to get away from the heat. So we shift to the other side. And as a result, A will go down, B will go down, and C will go up. And then the one that always gets everybody is pressure. If we increase the pressure, the equilibrium is going to be like, I can't take the pressure, man. Just can't handle it. I got to get rid of some of this pressure. Now, there's two things it can do. It can either shift to the right side, and the right side contains 2 moles of gas, or it can shift to the left side, and the left side contains 3 moles of gas. Which side shifting to will bring the pressure back down? Right, if you shift to the right side has less gas on it. Less gas exerts less pressure. So as a result, A will go down, B will go down, and C will go up. You'll use up the side that has more gas to make less gas, and that'll bring the pressure back down. How do you get molarity and molality? Well, you go to the store and you get it. Do you know the reference tables that we have available to us? What tables will give us all of our calculations for regions? T. So let's take a look at reference table T. It's a good question. Getting familiar with the reference tables is a very important part of how it goes. If you want to find the molarity, you just find it on reference table T. And what it is you take the number of moles of solute you have and divide it by the number of liters of solution. If you're given grams instead of moles, you have to convert the grams to moles by dividing by gram formula mass. For example, let's suppose we want to find the molarity of 20.0 grams of NaOH in 50.0 milliliters of solution. So we want to find the molarity of that. Well, molarity is equal to moles divided by liters. The only problem is we don't have moles and we don't have liters. So what we have to do is look up the formula masses of sodium hydroxide, and we also have to convert milliliters to liters. Well, that part's easy. Divide this by 1,000, you get 0.0500 liters. All right, 3 sig figs, and we keep those 3 sig figs. Now, NaOH has a formula mass of, well, sodium is 23.0, and then oxygen is 16.0. That brings us up to 39.0. And hydrogen is 1.0. That brings us up to 40.0. So what we do is we take the 20 grams, and we divide it by 40.0 grams per mole. Oh, that's convenient. That's 0.500 moles. I don't even need a calculator for this. Lucky day. Over 0.05 is 10.0, because 3 sig figs, and then this will be in moles per liter, or you can use capital M instead. Capital M is an abbreviation for moles per liter. Molar, moliter. Okay. Molality is exactly the same way, and if you want to find molality, you can find the equation on reference table AE reference table B. This is not a regions topic, this is just for this class only. Molality is exactly the same, except it's moles of solute, which you would get exactly the same way. If you had grams, you'd convert it to moles. Per kilogram, whoa, where are we? Yeah, here we go. Per kilogram of solvent. So what I would say up here is, I'd say 50.0 grams of solution. That would be 0.0500 kilograms. And then we'd solve it exactly the same way. Yep. Molarity and molality work the same way. Molarity is testable on the regions. Molality is only on the final. When given a reaction, how can you tell if it is endothermic or exothermic? Well, there's two ways. One, you'll either be given the heat on the left side or the right side. You can tell from that. Or you can simply look it up on reference table I. That's I as in... If you're given the reaction, A plus B plus heat forms C. The clue here is that heat is being absorbed as a reactant. Okay? In other words, this energy is not yet stored in the bonds of your chemicals. A and B don't have a lot of heat. C has got more. In fact, if you did this as a potential energy diagram, A and B would not have much heat, but C would have added that extra heat of reaction. And that's that heat of reaction right there. If it's like this, G plus Q forms H plus heat. That means G and Q had energy stored in their bonds. It's not stored in H, it's been released. So what it would look like is you'd start off with lots of energy for G and Q, and then H wouldn't have a lot of energy stored in it, and the difference, the amount of heat, that would be the heat of reaction. Okay, so that would be this heat that's given off. So you can tell in a reaction, if it's on the left side, if the heat's on the left side, it's endothermic, and if the heat's on the right side, it's exothermic. Okay? From reference table I, it's even easier to tell. On reference table I, they give you a list of many different reactions, from the combustion reactions on the top, to the synthesis reactions underneath it, to the solubility solution, they say the dissociation changes here, and acid-base neutralization on the bottom. And the best part is, it says right here, a minus sign indicates an exothermic reaction. So all you've got to do is take a look at the sign. If it's negative, you know you've got an exothermic change. So if they give you the heat in the reaction, you can tell from that. If they don't give you the heat, you can just look it up on reference table I and figure it out from there. How do you determine if it is polar or nonpolar? Well, not knowing what it is, whether we're referring to a bond or a molecule, I'll show you how we determine both. Let's suppose we've got this bond right here, a bond between hydrogen and chlorine, and we want to find out if that bond is polar or nonpolar. What we do is we go to reference table S and we look up the electronegativities of the elements in question. Hydrogen has an electronegativity on the next page. Let's try that again, shall we? Hydrogen has an electronegativity of 2.2, and chlorine has an electronegativity of 3.2. Now the difference between them, the electronegativity difference, is 1.0. Now any electronegativity difference that's higher than 0.4 is considered to be a polar covalent bond, which means that the electrons will be pulled towards the atom with the higher pull on electrons, higher electronegativity. On the other hand, if we have a bond between two chlorines, their electronegativities are both 3.2. So as a result, both want electrons equally strong. This would be polar covalent, and this would be a nonpolar covalent bond. And of course what we're referring to is this pair of shared electrons between each of the bonded atoms. The polarity of the molecule contributes to the polarity, the polarity of the bond contributes to the polarity of the whole molecule. For example, let's suppose we have carbon bonded to 4 hydrogens. Hydrogen has the lower electronegativity, carbon has the higher electronegativity. So the electrons in each bond are going to be pulled towards carbon. But because the pull is symmetrical in all directions, all of the polar bonds cancel each other out and make the whole molecule nonpolar. In this molecule, now we have 3 chlorines and a hydrogen. Hydrogen's got the lowest electronegativity of the bunch. Its electrons will be pulled towards carbon. But the chlorines have a stronger electronegativity than either of them. So the electrons will be pulled towards chlorine. This is not a symmetrical distribution of charge. So what ends up happening is this end of the molecule is partially negative, and this end of the molecule is partially positive. And because of this, we call this a polar molecule, because the distribution of charge is not symmetrical in the molecule. One side's got a stronger pull on electrons than the other, and it kind of looks like a mushroom. Let's suppose we have HCl, NaCl, and KClO3, three different compounds. A simple way of determining what kind of bond you have is simply to look at what kind of elements you have. For example, hydrogen is a nonmetal, chlorine is a nonmetal, and any bond between two nonmetals is automatically covalent. We can go further and say it's polar covalent because the END is greater than 0.4, which you've already figured out. Na is a metal, and chlorine is a nonmetal, and that makes the bond automatically ionic. Anything with an electronegativity difference over 1.7 is typically ionic. KClO3, though, is a weird case. We've got a metal, and we have two nonmetals. These two nonmetals are going to be bonded to each other. How? Covalently. But the metal will bond to the polyatomic ion to form an ionic bond. So this molecule has an ionic bond between the metal and the polyatomic ion, but the atoms in the polyatomic ion are bonded covalently.
Well, would we ever have to do like a dot diagram for that?
You would never have to do a dot diagram for a polyatomic ion. You know, that's beyond the scope of the course. If the molecule has two or more lines of symmetry, that means that the charge is symmetrical throughout the molecule. But if there's only one line of symmetry, that means that electrons are being pulled along that line of symmetry, making the molecule polar, giving one side a partial positive charge, the other side a partial negative charge. So the polarity of the bond comes down to the difference in electronegativity between two bonded atoms. The polarity of a molecule takes into consideration all the atoms and all the bonds in the molecule. It's been a long time since you've seen this. Miss it? How do you determine if a solution will have a low or high melting or freezing point? Okay. Whenever you add something to water, what ends up happening is it makes it harder for the water to boil or freeze. The molecules of water, when they boil, the molecules break free of their attractive forces and are able to go out into a vapor phase. And when water molecules freeze, they come together to form a nice regular shaped crystal lattice. And dissolving anything into the water will prevent the water from doing either thing, at least for a while. Now, normally, water is going to boil at 100 degrees Celsius, and it's going to freeze at 0 degrees Celsius. So normally, water has a range of 100 degrees where it's a liquid. But if you add a solute to it, that solute is going to attach itself to the water molecules. And just like if you tried to jump into the air with a cinder block tied around your foot, you're just going to need to jump that much harder to get up into the air. In order to get water to boil, when you dissolve something in water, you're going to have to heat it up. And the more stuff you put in it, the more you're going to have to heat it up. The more particles you have, the higher the boiling point will go. For example, a non-electrolyte like sugar, C6H12O6, will not have much of an impact on the boiling point because it doesn't break up any further than it already is. An ionic compound like sodium chloride, which breaks up to form two ions, will have double the impact on the boiling point. A molecule like calcium chloride, which breaks up to form three ions, will have triple the impact that sugar has. And a molecule like aluminum nitrate, which contains four ions, one of aluminum, three of nitrate, will have 4 times the impact that sugar has on the boiling point. So the more ions you put in, the higher the boiling point will go. And the exact opposite is true of freezing point. When you dissolve stuff in water, that stuff gets in the way of the water forming a crystal lattice. That means you're going to have to cool the water down more and more to get it to freeze. Now, the impact for boiling, and for those of you only taking the regions, I'm talking to the video, the impact, you don't have to worry about this, the impact is positive 0.52 degrees Celsius per molal of concentration. For freezing, the impact is a lot greater. It's 1.86 degrees Celsius per mole, going in the negative direction. So sugar is going to have a very small impact on the freezing point of water. Salt will have double the impact, table salt that is. And then calcium chloride would have 3 times the impact, and aluminum nitrate would have 4 times the impact. So the higher the concentration, the wider range of temperatures you're going to get for water being a liquid. Sugar has a wider range, salt has an even wider range, calcium chloride has yet even a wider range, and aluminum nitrate just has a crazy, stupid, wild range. And you expand the range where water can remain a liquid, both up and down. Yes, ma'am?
How do you determine if a substance has a high or low if it conducts electricity or low?
Okay. That's a whole different ballgame.
I know, it just made me think of that.
Okay. Whether it conducts electricity or not depends on whether you're putting charged particles into the water. What conducts electricity? Well, electrons conduct electricity. Why? Because they've got a negative charge, and electrons move a lot. And if you can get electrons to move, that's electrical flow. The other way you can get electricity to be conducted is if you have charged particles, like, let's say, sodium ions or chloride ions. And the only way you're going to get that is by either melting the salt or by dissolving it in water. Either way, the ions will break free of each other and be free to move around and carry their electrical charge with them. Okay? The other way you can do it is to have an acid. Acids are molecular, which typically don't conduct electricity, but when you dissolve them in water, the H from the acid bonds with water to form H3O+. And that's a charged particle, and so is the chloride, and it's free to carry electrical charge with it wherever it goes.
But I mean, like, when you put, like, how do you determine which one is the best conductor?
The best conductor?
Yeah, like if you have a number of substances.
If you're going to be given a multiple choice question, you'll have 4 choices. 3 of them will be definite non-conductors. Only 1 of them will be a conductor. For example, if we go back to our original question, our very first question that we did today, if you take a look at these, the question could also ask which of these is the best electrolyte, or which one of these is the best conductor of electricity. You've got 3 choices that are not ionic, nor are they acids. Only one of the choices is an acid. Okay. So these choices could also be used for a question like that. Yes, ma'am?
Do bases conduct electricity?
Bases, by definition, are ionic because they consist of a metal, like sodium, and non-metals, in this case, a hydroxide ion.
So,
if we take a look at choice 2, for example, you might say, aha! There's an OH there. But is it bonded to a metal? This bond is covalent, not ionic, so when you put it in water, it won't break up. Metal hydroxides do. Yes?
So are acids better conductors or are bases better conductors?
Let's suppose we've got a 1 molar solution of sodium hydroxide and a 1 molar solution of a strong acid like HCl. They will both be equally good as conductors because they'll put an equal number of ions into solution. Sodium chloride will put 2 ions into solution. Hydrochloric acid completely breaks up and puts 2 ions into solution. So acids and bases, one is not a better conductor than the other. When you start talking about, weak acids and weak bases, then you start talking about Ka and Kb, and that goes beyond where we need to be. Please clarify the effect of changing temperature on whether a reaction is spontaneous when only one factor is favored, enthalpy or entropy. Also, does this only happen at equilibrium? The answer to that is kinda. Here's how it works. Let's take this reaction. We have A gas plus B solid forms 2C gas plus heat. And if we take a look at what's happening to enthalpy, delta H, we'll notice that heat is being released as a product. That's exothermic, and nature favors that. Nature favors a decrease in potential energy. We're also going from a gas to a solid to 2 moles of gas. We got more gas flying around. That's a positive change in entropy. That's also favored. So as a result, this will always be spontaneous at all temperatures. Always be spontaneous at all temperatures. You don't even have to worry about equilibrium. Now, if you reverse this reaction, 2C gas, plus heat forms A gas plus B solid. Delta H now is positive. We're absorbing heat. That's unfavored. And delta S, we're going from 2 moles of gas flying around to only 1 mole of gas flying around. That's a decrease in the disorder of the system. That's also unfavored. As a result, this will be non-spontaneous under all conditions. Which makes sense. I mean, if going up a hill is not spontaneous, going down the hill would be. But what if we had a situation like this? What if instead it was A gas plus B gas plus heat forms 2C gas? Notice the difference. Now I've put heat on the left side. So what that means is that delta H is positive now. That's unfavored. Delta S is still positive. We go from 1 mole of gas to 2 moles of gas. And that's favored. So we could say it's sometimes spontaneous. And there will be a temperature where it reaches equilibrium. We just take whatever delta H is divided by delta S, and that'll give us a temperature at which it reaches equilibrium. Now, yes?
You said that it's A gas and B gas, so then it's 2 moles of...
Oh, did I say gas? Duh! Solid. Thank you. Okay, so yes, this is a solid, that's why, and that's why this applies the way it does. I was just trying to copy what was up here. And epic fail. Now, so let's take a look at this. How do you tell whether it's going to be spontaneous at high temperatures or low temperatures? Well, it all comes down to which factor is favored, and specifically delta S, because it's not just delta S, it's T delta S. Delta G, which ultimately decides whether a reaction takes place, is equal to delta H minus T delta S. Now, if T delta S is favored, the higher the temperature is, the bigger this number is going to be. As a result, this will be spontaneous at high temperatures. Because at high temperatures, the delta S factor is bigger and bigger and bigger. And since that's the favored factor, well, that's the way it's going to work. But what if it's the other way around? What if delta S was negative? Increasing temperature would make it an even bigger negative number. And that would make it even less spontaneous. So as a result, you'd want low temperatures for that. So it all comes down to what's delta S. If delta S is favored, you can make it even more favored by raising the temperature. If delta S is negative, then lowering the temperature will do the job. And you can see that in the solubility of gases. If you take a gas and dissolve it into water, this is a decrease in entropy. Nature doesn't favor that. Which is why gases become more soluble at low temperatures and less soluble at high temperatures, as seen on reference table G. Since dissolving a gas in water is not favored with entropy, at low temperatures it's more spontaneous, and at high temperatures it's less spontaneous. That's why gases have the curves they have. And that's why when you heat up something with a gas in it, the gas will come out. Whoever that was, did that answer your question? Yep.
Do you, when you want to know if it's spontaneous with high temperatures or low temperatures, do you just look at what delta H is? Or
Delta S.
Or, yeah.
Yeah.
Okay. So
Because
it's not
delta
like
S is what's being multiplied by temperature.
So it's not like if delta H was favored and delta S was unfavored, then it would...
Well, this only really works if it's sometimes spontaneous.
Mm-hmm.
If it's always spontaneous or never spontaneous, you never have to worry about equilibrium or whether it's spontaneous at high or low temperatures. Spontaneous is spontaneous no matter what the temperature is. I mean, you have to add activation energy to get the particles to collide to begin with, but once you accomplish that, it doesn't really matter what temperature you're at. For non-spontaneous, I mean, again, it doesn't really matter what temperature you're at. You're never going to get this to happen by itself.
Okay, so if like, but say if delta H was favored and delta S was unfavored, you would go by delta S?
You always go by delta S to determine temperature, because temperature is multiplied by delta S.
Okay.
The higher the temperature, the bigger the delta S factor is going to be. And the more negative it is, the less likely it is to happen. Yep. You're welcome. How do you tell if a reaction is spontaneous? Guess what? You just did it. Okay, next up. How can you tell if a reaction is spontaneous? I guess a lot of you had that concern. How do you tell, no, how does one find the isomer of one functional family to the other? Outstanding question. By the way, what is a pirate's favorite reference table? R. You'd think so, but it's really the C. Okay. Reference table R actually pairs the isomers up with each other. Alcohols are isomers with ethers. Aldehydes are isomers with ketones. Organic acids are isomers with esters. And amines are not isomers of amides, because amides have an oxygen that amines don't have. So if you want to find out something that's an isomer, all you have to do is just rearrange the structure. For example, let's suppose we have this alcohol here. Let's say we've got, let's do propanol. I like propanol. In fact, we'll make it 1-propanol or normal propanol. And we want to make an isomer of this. Okay, that's easy. The isomer of 1-propanol would be 2-propanol. Oh, but we didn't want another alcohol. We wanted, let's see, an ether. Ethers are isomers. Why? Because they both share a single bonded oxygen. Single bonded to something on one side, single bonded to something else on the other side. So, okay, we got to put this oxygen in between the two carbons. I gotcha. So we'll put one carbon here, that oxygen there, and then the other carbons there. So that we'll still have 3 carbons, and we'll still have 8 hydrogens, and we'll still have 1 oxygen. And so they're isomers of each other. Now, aldehydes and ketones are even easier, because the only difference between them is in an aldehyde, the double bonded oxygen is on the end, and in a ketone, it's in the middle of the molecule, primary versus secondary. So if we've got this isomer, let's say we have propanal, and there's really no other aldehyde isomer. I mean, aldehydes only have the one isomer. It's one, it's on the end. However, if we slap that double bonded oxygen in the middle, instead of having propanal, we would have propanone. So aldehydes and ketones are isomers of each other. The fun one is the organic acids and the esters. The organic acids and the esters both have a carbon that's bonded to 2 oxygens, one with a single bond, the other with a double bond. In an organic acid, that's at the end of the molecule, and in an ester, it's somewhere in the middle of the molecule. So let's suppose we had propanoic acid. Okay, that's propanoic acid. And we wanted to do an isomer of that. Well, there's no other place that we could put the COOH, because in propanoic acid it's always got to be on the end. But we can put the COO in between 2 carbons, like this. We just shifted this over 1 carbon. We still have 2 oxygens, 1 double bonded, 1 single bonded, on that same carbon. 3 carbons, and the same number of hydrogens in each, 6 hydrogens apiece. This would be called methyl ethano-8, because the eth part, the 2 carbon part, has the O in it. So that would be methyl, 1 carbon dingly-dangly, and the ethano-8 means that I needed ethanoic acid to make this ester. Yes, ma'am?
So for naming esters and ethers, do you go from right to left?
No, you do not. When naming an ether, you just simply name it for what's on either side of the oxygen, starting with the shorter chain. The shorter chain here is methyl. The longer chain here is ethyl. That's methyl ethyl ether. Here, this is methyl ethanoate because the part of the name that gets the O in it is the part of the molecule that has the double bonded O in it. The other side is methyl. Kind of like this was methyl here, this is methyl here. In fact, if you look at the example that's given on reference table R of our ester, methyl propanoate, here's the oxygen that splits it down the middle. The side that has the O gets the propanoate, right? 1, 2, 3, 3 carbons is prop. Propanoate. The other side's got the methyl in it, so methyl propanoate. Reading left to right doesn't make any sense because these molecules are three-dimensional. You can just simply turn them over, and now the left side is now the right side. So left to right won't work in this case. So that's why they had to come up with a special system to do it. Yep.
Can you go over like the dichloro, like adding in the di?
Adding in the dye? Well, you open up the vat and you pour in what you want, like blue or red or green. And oh, like the DI. Oh, okay. Let's see. Let's suppose we've got this molecule here. This is propane. And through a substitution reaction, we pull off one of the hydrogens and replace it with a chlorine. This then becomes 1-chloropropane. Let's suppose we carry out another substitution reaction and pull off another hydrogen and replace it with a chlorine. Now we have 1,3-dichloropropane because we have a chlorine on the first carbon and a chlorine on the third carbon. And since there's two of them, we put the prefix di to say that there's two of them. And a number to show us where each of those chlorines is located in the molecule.
Okay. What about 1,2-ethanediol?
1,2-ethanediol, also known as ethylene glycol, also known as antifreeze. It's in the name. Eth is 2 carbons. Ethan means they're single bonded. Diol means there's 2 OHs, one on the first carbon and one on the second carbon. So we have an OH here and we have an OH there, and the rest of them are hydrogens. Yes, ma'am?
Why is that one at the end and the other one in the middle? I mean, in the beginning? Like the diol and the di?
Oh, okay. The di tells you how many of a particular thing there are. There are 2 chlorines, so we call it dichloro. Here, there's 2 alcohol groups, so we call it diol.
Oh, so
If we called it diethanol, what that would mean is that we'd have 2 ethanols. I mean, I guess that would be the closest you could say to diethanol. I mean, you got an ethanol here and you got an ethanol there. But that's not even how this thing is named. This is called 1,4-butanediol. Because we've got 4 carbons, butane, single bonded, and there's 2 OHs, diol, and they're on the first and fourth carbons, 1,4.
So it's only when there's OHs that you do diol?
Well, if there's more than one OH, you call it diol. Here, in this case, if we have an OH, let's go back to this alcohol here. This is just called 1-propanol. There's only one OH, so we don't have to put a di or anything. Yep.
What if you had 3 OHs? Which is like
So let's suppose we have an OH here, and an OH here, and an OH here. This would be called 1, 2, 3, because they're on the first, second, and third carbons, propan triol, because we have 3 alcohol groups. Yeah. So we put the di or tri in front of whatever we have di or tri of. Alcohols are the only ones you have to worry about in this particular case. Like I said, right now there's over 7 million organic compounds that we know about with the potential for trillions more. And we're only investigating a small corner of it. Yep.
Last question.
Sure.
For diethyl ether, can you just write ethyl ethyl?
You can.
Okay.
Ethyl ethyl ether or diethyl ether, either one of them is acceptable. I mean diethyl because you have an ethyl here, you got an ethyl there, so diethyl, di! And of course you could also call it ethyl ethyl ether because there's an ethyl on either side of the oxygen.
Okay, thank you.
Yeah. Sorry for that. little outburst there. Anything else with this one? We've covered a huge amount of ground with this one question. How are monatomic molecules formed? Well, actually, it's funny. Monatomic molecules aren't formed. They just are. And the way it works is this. If you take a look, the definition of a molecule is a particle made of one or more atoms where you've achieved a stable octet. Now, if we take a look at hydrogen, for example, hydrogen has one valence electron, so it's not stable, it doesn't have a stable electron configuration by itself. It requires another hydrogen to share electrons with, and that's not monatomic, that's diatomic. The same thing goes for chlorine. Chlorine has 7 valence electrons, so it doesn't have a stable electron configuration. It needs to share electrons with another chlorine in order to achieve that. This would also be diatomic chlorine. But there are atoms that have a stable octet already without having to share electrons with anyone else. Which elements are those? The noble gases. The noble gases already have a stable octet, so they meet the definition of molecule. One or more atoms that combine in a way that gives them a stable octet. And they already have a stable octet, so they don't need to bond with anything else to achieve it. And helium only has one energy level. The first energy level can only hold 2 electrons, so 2 is a stable configuration for helium. And that's how the whole monatomic molecule business works. They don't really form because they don't have to. Diatomic molecules form out of a desire to share electrons to make a stable octet. But noble gases already have a stable octet, so they don't have to bond with anybody. How to find the charges of specific elements and molecules in a compound. For example, Cl and CaCl2, O2 too. Okay, this is a great one. I love doing these. It's like a little puzzle. Calcium chlorite, CaClO2, 2. And we want to find the charge of chlorine. Now, according to the periodic table, chlorine has a bunch of charges, and it even has more than the ones that are listed here. Chlorine can also be +3, but that's not listed here. And so we got to figure out which of these charges it is. Now, if the formula was just NaCl, that would be easy. I mean, Na is +1, so Cl has no choice but to be -1, because it's the only other thing there. But in calcium chlorite, it's a little bit more complex. Calcium has a charge of +2. Oxygen has a charge of -2. And if we want to find chlorine, we have to do a little bit of bookkeeping. 1 calcium with a +2 charge, 4 oxygens, each with a -2 charge, gives you a -8 charge. And when you add all these up, they have to add up to 0 because compounds are neutral. So what has to go here? A +6. Now that +6 is going to be divided between the 2 chlorines that you have in the compound, meaning that each chlorine's charge is going to be +3. Yes, ma'am?
On reference table, it says chlorite has a negative charge.
Okay. You can also do it that way. You can ignore the calcium entirely and you can just solve from chlorite. Chlorite has a -1 charge when you combine the chlorines and the oxygens together. Each oxygen is -2 for a total of -4, which means that chlorine has to be +3 for the whole thing to add up to -1. So you could do it that way also. Yep. You could either do it with the calcium or you could do it without the calcium. With the calcium, it adds up to 0. Without the calcium, it adds up to whatever the charge of chlorite is, which, as you said, can be found on reference table E. Oh, where's my table E? Yep. What is the I in the equation for the boiling and freezing point depression constants? Okay. I'll just leave that up here. Now, let's suppose we have solutes like NaCl, CaCl2, Al, NO3, 3, or C6H12O6. When we dissolve these in water, are they going to have an equal effect on the freezing and boiling point? In fact, we saw that earlier when we looked at those 4, that the one that breaks up into more ions is going to have a much bigger effect than those that break up into fewer ions, or those that don't break up into ions at all. So what the I factor is it's called the Van Hoff factor. And what it means is how many particles does it break up into when you dissolve it in the water. So in this case, I would equal 2. 1 for the sodium and 1 for the chloride. How many particles does this break up into? So the I in this case would be 3. Here, how many does this break up into? 4, so a lot, yeah. Well, you know it only breaks up into 3 because how are the nitrogen and oxygen bonded? Covalently, right, and that doesn't break up when you dissolve it in water. So you'll get 1 aluminum and 3 nitrates. And this, it's all covalent, doesn't break up at all. What would I equal? 1, exactly. So that you can show the impact of having more ions on the freezing point or boiling point. And this, of course, would be 0.52. This would be 1.86. This is the molality of the solution. You can find the equation and the constants. The equation can be found on AE reference table B. And it even says here, I equals the number of dissociated particles. And up here, it gives you the boiling and freezing point constants that you can plug in for KB and KF.
Could you repeat why, on the other page, why the last one was 1?
Okay. When you dissolve things in water, only 2 kinds of substances break up further into ions. First, ionic compounds. Ionic compounds are made up of metals and nonmetals. Now the nitrate is just, nonmetals, so that just breaks up like this. This is all nonmetals. Nonmetals don't break up when you put them in water.
Oh.
And so it won't break up any further. Yep.
For the molality, will they usually give you the molality?
Yeah, they'll usually give you the molality. Exactly. And usually it'll be a 1 molal solution of non-volatile non-electrolyte. And of course, if it's a non-electrolyte, that means it's something that doesn't break up into ions, so you don't even have to worry about I. I will equal 1. In my case, I equals 2, and for you guys too. I equals. You can't see this on the camera, it's hysterically funny. Okay. How do you figure out the freezing boiling point of a substance? Guess what? We just did it. Next up. When given a compound, how can you determine its freezing point and boiling point? I'm sensing a theme here. How can you go over how to draw dot diagrams of different compounds such as metal to nonmetal and nonmetal to nonmetal? So what we're looking for here is ionic bonding and covalent bonding, the dot diagrams. And the dot diagrams are based on the fact that the 2 kinds of bonds are completely different. For example, in a covalent bond, electrons are shared. In an ionic bond, electrons are transferred and not shared. If we have oxygen, which has 6 valence electrons, if we bond it with another nonmetal, like hydrogen, well, they'll just share their unpaired valence electrons, because sharing is caring. On the other hand, if we bond oxygen, which has 6 valence electrons, with a metal like sodium, the oxygen is going to seize the opportunity to gain an electron from the sodium. Of course, it'll need a second sodium to get its second electron from. And what will happen is the oxygen will become a -2 oxide ion. The sodiums, without any dots, become +1 ions. And that would be for an ionic bond, to represent the difference between sharing unpaired electrons to make shared bonds, and just an outright transfer of electrons to give you separate ions that are not actually physically connected.
Does it matter if you put it NaO, Na, or can you put it like Na, NaO?
Why do we put the Na here and not next to each other? Right, Na is positive, this Na is positive, they're going to repel each other, but they're both attracted to the negative oxygen. Opposites attract. Yes, ma'am?
You don't have to write it in a bent format like you do the...
No, the structure you get in the molecule is going to determine where the electrons are shared. Since there's no sharing going on here, they're just going to form a crystal lattice. This will be an oxygen ion, oxide ion. This will be a sodium ion. That'll be another sodium ion. And then you'd have another sodium ion here. You'd have another sodium ion here. You'd have another oxygen here. You'd have another oxygen here. You'd have... You see what I'm saying? It would be in a crystal lattice. It wouldn't be in a nice structured particle like this tipped over Mickey Mouse right here. What are the characteristics of metals, nonmetals, and metalloids? We take a look at the periodic tables, and we can see some differences right away. Metals always form positive ions. And how do you become positive as an ion? By losing electrons. So metals lose electrons. Metals very easily lose electrons. In fact, they lose electrons to each other, allowing metals to conduct electricity throughout them. So metals also have low electronegativity. In order to lose electrons, their hold on electrons is not very tight. So they also have low ionization energy. It doesn't take much energy to take an electron away. The properties of elements are dependent entirely on their electrons. Nonmetals, on the other hand, having a much greater nuclear charge compared to the metals with the same number of energy levels, are a lot more attracted to their valence electrons and to the electrons of other atoms. So they tend to be smaller, their electrons are closer to the nucleus, so they're more attracted. And they also form negative ions. And they form negative ions by gaining electrons. Okay? So nonmetals gain electrons and become negative in charge. Although sometimes, especially if they bond with another of their own kind, they can share enough electrons to make a covalent bond. The metalloids are kind of in the middle. For example, silicon conducts electricity like a metal sometimes, is sometimes an insulator like a nonmetal. The reason nonmetals don't conduct electricity is because when they form covalent bonds with each other, like O2 and Cl2, the electrons are locked in place and are not free to move around, so they can't conduct electricity. Whereas metals, their electrons freely move from one atom to the next, allowing them to conduct electricity. Metals are shiny, nonmetals are dull. Metalloids tend to be shiny. Metals are malleable, which means you can bend them, you can roll them into thin sheets. Nonmetals are brittle. Metalloids tend to be brittle. So they share characteristics of both metals and nonmetals. And those are the differences between the three different kinds of elements. And of course, the fourth element, the aloof ones, the noble gases, don't associate with anybody because they already have a stable octet. And I've already got what I want. What do I need to bond with you for? You bring nothing I need.
Question on the big final, it's like, what is the conjugate acid of HSO3? How do you find like a conjugate acid?
The conjugate acid is easily found simply by looking it up on AE reference table E. AE reference table E lists conjugate pairs. For example, I-1 is a base, its conjugate acid is HI. HCl is an acid, its conjugate base is Cl-1. HSO3-1 as a base will have the conjugate acid of H2O plus SO2. So you just have to look up whatever's on the opposite side. Yes, ma'am?
What does it mean if they show up on both sides?
That means it's amphiprotic, and depending on the situation, can act as either an acid or a base.